Okay, thank you very much to the organisers for the invitation. Yes, I'd like to do something that is slightly unusual in my talk today and talk about something that I myself have had nothing whatsoever to do with. This is Bob Hough's work. So the title is Bob Hough's Solution of Erdős's Covering Congruences Conjecture. So this came out on the archive around about that crazy time last year when people were just proving everything. Sometime around, I think this one was June of 2013. So this was one of, if not Paul Erdős's very favorite problem. And the statement of Hough's theorem is as follows. If the positive integers z, so if z is covered by congruences of the form a to the m mod m, so this is called a covering system of congruences, but you're only allowed one for each value of m. Oh, and you're also only allowed finitely many of them. And then the conclusion is that one of the moduli m has got to be smaller than some absolute constant. So one of the m's is at most, and I think his most recent bound is 10 to the 18. So Erdős asked, is there a covering system of congruences, that's one of these objects, finitely many congruences, one for each m, with all of the moduli sufficiently large, larger than some pre-specified bound. So Hough has shown that the answer to that is negative. So this answers Erdős's question negatively. So maybe I'll just, I'll start actually by explaining a little bit about the history of this question and where this notion of covering congruence comes from. And I'd like to thank Kevin Ford for explaining this to me. Is Kevin here somewhere? Yes, there he is. And also I blame him for any errors that I'm about to make in this. So it has to do with the theorem of Romanoff from about 1934. And Romanoff proved that the numbers of the form prime plus a power of 2, p plus 2 to the k, have positive density, positive lower density, I guess, in the integers. So a positive proportion of all positive integers are prime plus a power of 2. But in the opposite direction, you might ask which numbers are not of this form, and it was a question. I mean, it's fairly clear that most even numbers are not going to be of this form. But what about the odd numbers? So is there an infinite arithmetic progression of odd numbers not of this form? And it turns out that there is, and to construct it, so to construct one of those, we're going to use a covering congruence, a system of covering congruences. And that's good because I haven't actually shown you any system of covering congruences yet. So the answer is yes. And uses a system of covering congruences. Probably I should say covering system of congruences, but never mind that. So here is an example of such a thing. Indeed, the system 0 mod 2, 0 mod 3, one mod 4, 3 mod 8, 7 mod 12, and 23 mod 24. So that is a covering system. And the proof of that's trivial. You need to just check the numbers up to 24, and it's a very short check. I actually did that myself. So didn't trust Kevin entirely on that one. But the point is that those congruence conditions tell you some other congruence conditions about 2 to the k. And those conditions are as follows. So if k is 0 mod 2, then 2 to the k is 1 mod 3. And 1 mod 7. 2 mod 5. 8 mod 17. 11 mod 13. And 2 to the 23 mod 241. So here I am trusting that Kevin's informed me correctly. Now the thing you'll notice that these are all different primes. So what I can do is I can pick x by the Chinese remainder theorem. So suppose that x satisfies these congruence conditions. So that will be modulo 3 times 5 times 7 times 13 times 17 times 241. Then x minus 2 to the k is going to have a hard time being a prime. So x minus 2 to the k is always divisible by one of those primes, 3, 5, 7, 13, 17, and 241. So that almost answers the question, except of course x minus 2 to the k could be equal to one of those primes. But then you can find another arithmetic progression that never contains 2 to the k plus 3 or 2 to the k plus 5 and so on, and then you're finished. So this is really just a historical point, because actually there's no very close connection between covering congruences and these Romanov numbers, because actually here I use some quite specific properties of this specific system of covering congruences. The fact that you can get distinct primes in here. But somehow, I guess when Erdős was thinking about this, this made him think of this notion of covering congruences for its own sake. And then he started asking these questions like the one that Bob Hough has answered. Okay, so previous work on the problem, I mean, I've shown you one example of a covering system, but remarkably, there are actually covering systems there are systems of covering congruences with rather large moduli, all with moduli at least 40. And this is a result of Pace-Nielsen. And I have to admit I've not looked at that. I assume there's quite a lot of computation involved in that. So what this means is that there's a constant out there to be determined that's between 40 and 10 to the 18. So it's an open question. What is the largest possible minimum modulus of a covering system. So let's call that m0. So it's going to be between 40 and 10 to the 18. So it seems to me like a polymath project waiting to happen. Right, so what I want to do in the rest of the talk is to try and give you the main ideas of Hough's proof of this statement. And this is not especially easy to do because it really is quite a difficult argument, but hopefully I'll give you some of the flavor of the argument and try and explain what the new bits of it are and what the key ingredients are. So here's Hough's argument. So I should say before I forget that some parts of Hough's proof are motivated by earlier work by 5 authors, Filosetta, Ford, Konyagin, Pomerantz, and Yu. So again, I haven't looked at that paper, but my impression is that it proved results of the form. If you have a covering system, then it has to have many different moduli in it. So they proved lower bounds for the sum of the reciprocals of those moduli. And furthermore, they introduced 1 or 2 ideas that Hough also uses that had not previously been introduced. So first of all, we're going to think of, so let's imagine that we start with all of the integers, z. So we start with z, and we're going to think of this as a kind of a sieve. So we're just going to remove a congruence class mod m. So remove, or sieve, that's the standard term, by the congruence class am mod m for each m in curly m. So curly m is going to be a finite set of moduli. And what we're going to show is that if all of those moduli are large, let's say bigger than 10 to the 18, although the arguments I'm going to show you wouldn't give 10 to the 18. So the aim is to show that if you do that sieving by those congruence classes, you end up with something at the end. Aim is to show that what is left is non-empty. And if you can do that, then you'll have proven Hough's theorem. So the first key idea is that sieving is going to be done in stages. So we're going to fix once and for all some series of thresholds. And they're going to be called P1 less than P2, less than P3. And one of the difficult things about the argument is trying to explain why there's a choice of various parameters that I'm going to have to mention that actually works. But let me just tell you so that you get an idea what these thresholds will be. So P1 will be something large, I don't know, 10 to the 10 or something. And then each Pi will be basically exponentially larger than the previous one. So Pi plus 1 would be e to the Pi to the 1 over 100 or something like that, say. So this is just to give you an idea. It's a pretty rapidly increasing series of thresholds. And then you do the sieving. You're first of all going to sieve by all of the things, all of whose prime factors are less than P1. But actually in describing this, I'm going to make a simplification. So we'll simplify a bit. And assume Well, we'll assume that all of the moduli are square free. And that's advantageous because it means that this first sieving process, where I remove all of the moduli which are P1 smooth, all of the prime factors less than P1, that's just a bounded number of P1s, independent of anything about the set M. So the ith sieving process, so the first sieving process, is remove all congruences with M divisible by only primes P that are less than or equal to P1. So I'm going to call that set, call these M's curly M1. And then the second sieving process well, now you get to remove all of the congruences whose modulus is divisible only by primes up to P2. So remove all new congruences with M divisible by primes P less than or equal to P2. So call the set of these curly M2 backslash curly M1. So curly M2 is the set of all moduli which are P2 smooth, and so on. And because the set of congruences is finite, at some finite point, the ith sieving process will have exhausted all of the congruences we have in our set. So at some finite stage, curly mi equals curly m. That is to say, we have removed all of our am modulo m for m in curly m. Oh. How do I, is this manual? Oh, okay. And in fact, Hough gets an explicit lower bound for the density of things that are left after the ith sieving process. So let me write that at the bottom here, actually. So in fact, Hough proves that the density of integers remaining after the ith process is at least, well, it's something that's positive. So we'll actually sketch a proof that it's at least e to the minus log squared pi. So that's enough. It's just, in particular, is positive. So completely crucial to understanding how this works is to understand how the sieving process, how say, once you've done the first sieving process, what the set of congruences you're left with looks like, and then how the second sieving process affects that. So I'm going to illustrate that with just an example. So let's suppose that P1 is 3, which it's not, but let's suppose it is, and that P2 is 7. And suppose the first sieving process removes let's say 0 mod 2, and maybe 0 mod 2 mod 3, and 5 mod 6. So I think that just leaves, it leaves a set that's periodic modulo 6, and it only leaves the element 1, I believe. So 0, 1, 2, 3, 4, 5. And actually, the only thing that survived this sieving process is the element 1. So that survived. Now, what happens next? Well, the number of new congruences that I'm going to sieve by in the second sieving process, that's all congruences which are square-free, to moduli that are square-free, and all the prime factors are at most 7. So there will be actually 12 new congruence classes. But I won't list 12 congruences. I'll just list some examples. So suppose that the second sieving process removes 3 mod 10 and 5 mod 14. So let's say 3 mod 21 and 6 mod 35, 35. So what effect will that have in this picture that I've given here? So this will leave some residue classes. So this leaves residue classes modulo 210, which is 2 times 3 times 5 times 7. So this is Z mod 6Z. And I'm going to think of Z mod 210Z as fibered above Z mod 6Z. So these, I'll call these fibers sort of F3, F4, etc. And each of those fibers is isomorphic to Z mod 35Z. So what does the congruence condition 3 mod 10 do? Well, if you're 3 mod 10, then you are 1 mod 2, obviously. So potentially you affect the fiber above 1, and the fiber above 3, and the fiber above 5. But actually, the fibers above 3 and 5 have been eliminated already in the first sieving process. So what happens is that you end up sieving only in the fiber above 1, and the congruence condition you have there is 3 mod 5. So I don't know why I'm going to write this. So this sieves by 3 mod 5 in F1. And what about 5 mod 14? Well, again, 14 is 2 times 7, so it could affect 1, 3, and 5, but again, only 1 is left in. So this will now sieve by 5 mod 7 in that fiber. Now, 3 modulo 21, well, if you're 3 mod 21, then you're 0 mod 3. And so you can only affect the fibers above 0 and 3 in Z mod 6. And 1 is not one of those fibers. So the condition 3 mod 21 doesn't affect F1. So there's no effect at all. And then 6 modulo 35, well, that doesn't imply any congruence conditions modulo 6. So it actually affects all of the fibers. And in particular, in the fiber above 1, it's just the same condition, 6 mod 35. So when you do the second sieving process, it has the effect of doing separate sieving processes in the fibers, which are isomorphic to Z mod 35Z. And somehow it's crucial, this point that I've hopefully illustrated here, that not all of the new congruence conditions will affect all of the fibers. So a given fiber, and I've only got one in my picture here, will only be affected by some of the congruence conditions. Ah, stop. So if anyone has any questions, by the way, now's a good point to ask, because I'm going to do some erasing. Were there any? Okay. Yes, I am, exactly. So I'm assuming that, but it's going to be rather difficult for me to tell you where I'm using it, other than that obviously some of the assertions I've made must be false if I don't assume it. And of course, the example I just showed you blatantly does not assume that. But I can't do arithmetic mod primes that are 10 to the 18 at the board. So I'm going to try and show you a heuristic for how one would expect this fiberwise sieving process to work. So suppose that after the ith sieving process, we're left with a set Ri contained in Z mod Qiz of residues. And here Qi will be the product of the primes less than Pi. And given, well, so now suppose we do the I plus first sieving process. So consider now the I plus first sieving process. Each modulus that is relevant there, so if m is in curly m sub I plus 1, but not in curly m sub I, then it can be factored as, so m equals mi times q, with mi in curly mi, and q is in what I'm going to call curly n I plus 1, which is the set of all things, all of whose prime factors are between pi and pi plus 1. So this means if p divides q, then pi is strictly less than q, less than or equal to pi plus 1. So we've kind of, I did that without saying that I was doing it here. For example, when I was looking at the congruence condition modulo 14, I observe that 14 is equal to 2 times 7. So this is the 2, and this is the 7. And what I ended up with was a congruence condition mod 7 in the fiber. So let me write, so this will gives a congruence condition modulo Q mod Q in each fiber FR, where R is in the set R is congruent to AM modulo MI. And the number of such R is going to be QI over MI. So for example, the number of things mod 6 that are congruent to 1 mod 2 is 3. So now I can kind of use this to get a heuristic for how much sieving I expect to do in a given fiber. So let's write x sub q of R for the number of congruence conditions congruences modulo Q which affect the fiber over R. Oh. So I can at least figure out the average of this. So then the average, 1 over Qi, times the sum over all R in Z modulo Qiz of xq of R. Well, it's a double count. So for each value of mi, I get Qi over mi values of R. So this is just the sum over mi in curly mi of 1 over mi. But curly mi is just the product of, it's the set of all things which are products of primes less than pi. So this will be the product over p less than pi, 1 plus 1 over p. And as is well known, this is a constant times log pi. So what this means is that I should expect to sieve for every q and for every fiber, I should expect to sieve by log pi residue classes mod q. Mod q in each fiber. Fr. Now, of course, that's not going to be literally true, because as we saw in the example here, I mean, there were some fibers that were not affected at all, and some were affected by several congruences. But let's just accept this as a heuristic for now, and try and pursue it. So let's make the totally unwarranted assumption that that is literally true for all q and for all r. So well, even though it's just an average statement. So suppose this is really what happens. For all q and all r. So that's assumption 1. And now let me make another completely false assumption, a completely unjustified assumption. Let me also suppose that when I sieve by a congruence mod q, and then I sieve by another congruence mod q primed, that those things are independent operations. So suppose also that sieving by congruences mod q and mod q primed are independent operations for all distinct q and q primed. So we know that's not the case. I mean, if I remove the residue class 1 mod 10, and also, well, the residue class 1 mod 10 is not independent of 1 mod 14. So they both imply that you're an odd number. But if q and q are co-primed, then something like this will be true. So two big assumptions. Let me see what I can get from those two assumptions. So what should I expect? So how much is left in the fiber FR after the sieving? And so the answer is I'm going to be left with the density of things that's left. We'll have the product of 1 minus xq r over q. So I'm removing xq of r residue classes mod q for every value of q. And so the proportion of things that's left is 1 minus that fraction. And I take the product over all q divisible only by primes between pi and pi plus 1. So the density would be this. And you can figure out what that is. I mean, I'm being very rough here. Roughly exponential of minus the sum of xqr over q. But the sum of xqr over q, well, that's roughly log pi times the sum of 1 over q, because I'm assuming that the number of congruences that I'm getting rid of is log pi, and this is going to be roughly log pi plus 1, again by straightforward computations. So I expect to be left with a set of density something like exp of minus log pi plus 1, or at least some constant times that. And what you might notice is that that's way bigger than what I'm actually hoping to prove. So I claimed that after the ith sieving process, we're left with a set of density e to the minus log squared pi. So I'm allowing myself to lose a huge amount from this rough heuristic. And of course, where I'm losing things is that neither of these assumptions is justified. So what I have to explain to you is how Bob Hough gets around the fact that neither of those assumptions that I use in this heuristic is literally true. So the first one is really kind of difficult to explain. And as such, I'm not going to explain it properly. So my heuristic was based on just an average. So I told you what the average number of residue classes that you remove in fibers is. But by a more elaborate analysis, you can get at least a moment estimate. So to deal with assumption 1, Hough relies on a moment estimate so that would be something of the form average value over R in the set of things that survive the ith sieving process. Actually, I didn't introduce a name for that. I'll write that in a moment. xq of R to the t. So you need an estimate for something like this, being bounded by basically log pi to some power. So Ri subset z mod qiz is what survived the ith sieving process. Now here there's a technicality that's really difficult to explain, but also somehow crucial. I don't want to show you how you get this moment estimate, but to get it, you need to assume that this set Ri of residues that survive the ith sieving process is what's called regular. So this must be regular, and that's a technical thing. But it kind of means reasonably well distributed in certain residue classes. And actually, also it's got to be quite uniformly fibered over Ri minus 1, but some technical conditions. And so to make the whole argument work, you have to include this notion of regularity in the induction. So whereas I said, right at the top up there, I said that we show that the density of things that survives the ith sieving process is, wow. The density of things that survive the ith sieving process is e to the minus log squared pi. You actually got to show that there's a regular set of things of that size surviving the process. So there's a sort of complicated double induction. You show that many things survive the sieve, then you regularize, and then you sieve again, then you regularize again, and so on. And it's technical, but it's necessary there. What I want to devote a bit more attention to is how, somehow this assumption 1 I made, namely that the generic behavior in fibers is close to the actual behavior for each fiber, that's sort of believable. But the second assumption I made, namely that sieving by congruences to different moduli are independent, that's just obvious nonsense. It's not true. Hang on, which one can I? So recall that the moduli that we're sieving by, in the I plus first sieving process, we sieve by congruences mod q, where q is going to be lying in this set curly n I plus 1, which is things with prime factors in the range pi less than p less than or equal to pi plus 1. Now, a typical pair of elements from there will not be coprime. In ni plus 1 will not be coprime. So what Hough does is he partitions that set of congruences into 2 bits. So the idea is to partition curly n sub I plus 1 into a small part and a large part. Oops. And these are given by some threshold. So this means that q is less than some threshold ti plus 1, and here that q is bigger than some threshold ti plus 1. And again, those thresholds you have to choose, and it's not obvious that there's a choice that works, and I'm not going to tell you what the choices are because I don't think it really illuminates things. But they can be chosen in such a way that a typical pair of q and q prime from in there really are likely to be co-prime. So a typical pair q and q primed in here are co-prime. And that's intuitively reasonable because those numbers are expected to have not very many prime factors. And so that it's pretty likely that the sets of their prime factors will be disjoint. And then this set here, the set of large values of q, well, it turns out that you can just handle that trivially by... so each of the q's in here, although each of them's big, so when you sieve by a congruence class modulo q, you don't do very much. You just remove 1 over q of the elements in the fiber. So this gets handled trivially for some definition of the word trivial. But what I want to focus on is what happens in here. So now what we've focused in on now is a kind of a sieving process where you're removing congruences modulo q's and q primes. And usually those q and q primes are co-prime, but not always. And there's a tool in combinatorics that's perfectly designed to handle that sort of thing, and that's called the Houghs local lemma. So to handle the sieving inside ni plus 1 small, we use the Houghs local lemma. So I'm going to tell you what the Houghs local lemma is in this setting. So I'm first going to tell you a weighted form of it, which I find completely unintuitive to explain the content of, but it's sort of essential to formulate this form for the proof. So what it states is, suppose we have events. Let me start a new board for this, actually. So, Houghs local lemma, LLL. Suppose we have events AQ in some probability space. So the Q's are the same as the ones that I've been talking about. And AQ is independent of all AQ primed, apart from just a small set of Q primes, unless Q primed lies in a set gamma of Q. And when I say independent of all of them, I mean independent of the sigma algebra generated by them. So suppose the following completely unintuitive condition holds. So suppose there are weights xi, or xq in fact, between 0 and 1, such that the probability of AQ is at most xq times the product over q primed in the bad set for q of 1 minus xq primed. So I will explain which weights to choose, which will make this look a bit nicer in a moment. Then, and here's a really crucial point. So there's a certain statement of this that's usually in the literature, but there's a slightly generalized statement which is absolutely fundamental to Hough's argument. So I'm going to give you this generalized statement. So whenever V is contained in U, are sets of indices, it's the probability that none of the AQs in V happen is at least the probability that none of the AQs in U happen times a certain product. So the product over all Q in V but not in U of 1 minus XQ. Okay, so let me explain what on earth this is supposed to mean. So as I said, the formulation like this is crucial to the proof. So if we take, let's take XQ to be twice the probability of AQ. Then I can prove a theorem of the following form. So this is a theorem. So it's basically just a reformulation of a particular case of Lovász local lemma. So suppose that the assumptions are as above. So suppose AQ is independent of AQ primed with Q primed not in a bad set. And suppose that the total probability of the bad set is at most 1/10. For every Q. And then the conclusion is that the probability that none of the AQs happen is at least e to the minus 4 times the sum of the probabilities of the AQs. So this is really quite close to the naive heuristic in which the AQs, well, if the AQs are always independent of the AQ primes, then you get this without the 4, basically. So that's the heuristic I applied earlier. What is the value of XQ? Twice the probability of AQ. Yeah, they're going to be, in practice, they'll be incredibly rare events. I mean, whenever I'm going to apply it, they'll be absolutely incredibly rare events. Yeah. Furthermore, we have that the probability that none of the AQs happen is at least 1/2 times the probability that that none of the AQs happen, and that Q is not in some exceptional set if S is small. S is a small exceptional set. In fact, with the sum over Q in S of the probabilities being at most 1/10. So these are just straightforward applications of the Lovász local lemma, straightforward substitutions into the first statement. This one here is kind of a well-known sort of thing. So basically saying that if you've got some almost independent events, then the probability that none of them happen is close to the naive heuristic. That's what the Lovász local lemma usually does for you. But this second thing here is less well known. And what this is saying is that basically, in addition, so if you look at the probability that none of the events happen, but if you just don't include one or two of those events, then that really doesn't change the probability by very much, just by at most a factor of 1/2. So this could be called a relative Lovász local lemma. And well, it's the first part, the well-known part is what controls. This tells you that when you do the I plus first sieving process, you still have lots of things left at the end. But it's the second part that tells you that you can make the things that you have left at the end regular in the technical sense that I didn't tell you, that's necessary to make the whole induction work. So to summarize, Hough's argument is an iterated application of the Lovász local lemma, in which after each application of it, you have to do a certain regularization to make the next application work. And what controls the regularization is this not so well-known relative version of the Lovász local lemma. And I think that's about as much as I can reasonably say on the topic, so I'll stop there.